one of the most important themes in metabolism is that you're going to take a energetically unfavorable reaction, you're going to couple that with a energetically favorable reaction. And in this context, the most important energetically favorable reaction that we're going to use is the hydrolysis of ATP. So let's just kind of talk about ATP hydrolysis and what we can say about this. So this, the reaction itself has a very negative value for its delta G. Its equilibrium constant in this context is going to be pretty large. And this, what I mean by that, if you remember back to chemical kinetics, I mean that it's large and that it's greater than 1. Also not superbly important, but remembering that magnesium as well is always going to be coupled around there whenever we have ATP being hydrolyzed to stabilize its transport, because ATP is not the most stablest of molecules. It's not the most unstable, but it's also not the most stable. So let's just say that we have a hypothetical situation where we have a reaction of A reacting with B. We're keeping this stuff abstract, and it's going to react in equilibrium, of course, to give us C. And for this reaction here, let's just say that for whatever reason, I'm going to keep this abstract. I'm not going to give specific values, but if you would like to, you could look up specific values of reactions where ATP is used. But let's just say for the purposes of this has a positive value for its delta G, and the KEQ value for it is less than 1. So for this reaction, right, this is not energetically favorable, and I want to make it energetically favorable because I need to do this reaction. I have to in order for my cells to exist at all. So the way that I'm going to do this is I'm just going to add, I'm still going to have A plus B, but I'm just going to go ahead and include in this reaction the hydrolysis of ATP. And just like before, this doesn't really change the overall reaction directionality of it so much, because in terms of with respect to the A and B, but what this does change is the overall delta G values, because we're now considering ATP as a part of our reactants and a part of our products. So if we were to draw a reaction coordinate, we would draw the reactants being in a higher energy state and then the products being in a lower energy state, right? It's because it's not like we're focusing on an individual reactant or an individual product that's being formed. No, no, no. When we draw these reaction coordinates, it's reactants, plural, and products, plural, all right? So this reaction here, now that we've added ATP in this usually is going to give us, because ATP is such a endothermodynamically favorable product here, it's going to now have a delta G value that is negative, and it's now going to have a equilibrium constant that is going to be large, right? That equilibrium constant is now going to be greater than 1, or at least increased in some magnitude. So one of the things that people always think about, and I've always thought about, is why it's specifically our cells have evolved the use of ATP. Why not other molecules? And that's because if you were to look at, and this is in your textbook as well, standard free energies of hydrolysis of other phosphorylated compounds, you notice that ATP is kind of like right in the middle. So if I were just to kind of draw some examples of this, so phosphophenol pyruvate, which I'm going to abbreviate as PEP, this gives off of around, upon hydrolysis at least, about negative 62 kilojoules per mole. Creatine phosphate, which I'm just going to go ahead and abbreviate that as CP, this guy is going to give off anywhere about negative 43 kilojoules per mole. These are all just speculative theoretical yield amounts here. But if I were to look at ATP, and if you were to look at ATP in your little chart diagram that you have here, ATP gives off of around 30 kilojoules per mole, about 30.5, and I'm not really stressing the numbers here in an extreme context here. But the other molecules that we have in our body that are phosphorylated would be like glucose 6-phosphate. Glucose 1-phosphate, whenever this guy is hydrolyzed, or whenever the phosphate group is hydrolyzed off, this gives us about 20 kilojoules per mole. And then lastly, I'll just list G3P, which glycerol 3-phosphate, which gives off about negative 9 kilojoules per mole. So why ATP? Why not phosphoenol pyruvate? Why not creatine phosphate? Why not, and I didn't list it on there, 1,3-BPG? And that's because if you were to look at this, that a spontaneous reaction is just that. It's spontaneous. It's prone to happen pretty frequently. We are using something that we need to, one, that's going to give off a lot of energy, but two, isn't going to explode within seconds of making it. And so ATP is just right. It's perfectly in the middle to where we can use it as an energy source. It's stable enough for us to move it about from one organelle to the next. And at the same time, it's also going to give off just the right amount of energy that we need to work things out. So if we were to say, consider a cell that used phosphoenol pyruvate or creatine phosphate instead of ATP, that cell ultimately would not be able to get a high enough energy yield to be metabolically efficient. So before I talk about the actual hydrolysis, I'm going to really make a note of two things. The first thing is the actual structure of ATP itself, and then consider the factors that contribute to the stability of its product. So for the structure of this, whenever I like to draw ATP, I always for some reason start off with drawing my sugar for it. And if you remember whenever we were drawing DNA, or I think even when we talked about drawing sugars, it's a furopyranose. There are better pictures out there on the internet, I promise you. Alright, so yeah, it's a little cramped in there, but anyways, I guess cramped nature of this kind of just reiterates the cramped frustration of the phosphate molecules that they feel in this. So if we were to look at this, on each and every one of these oxygens here we have, and I'm drawing it as the resonance hybrid form, so there's a negative formal charge for each and every one of these, and then for the last two, because there's the extra that are unbound, if we were to go ahead and just like look at it in terms of formal charge, this is -2. So this overall structure of this has a -4 net formal charge, right, which is really unstable, right? Like we've seen in organic chemistry, the things that can happen from things that have a -1 net formal charge. So this structure here is going to contribute a lot of it. So thinking about this and what the product is of our hydrolysis product, whether it be adenosine diphosphate or adenosine monophosphate, kind of gives some leeway into why ATP hydrolysis is the favorable reaction that it is. So the first thing that really contributes to the stability of the products, but it's not really so much that it's contributing to the stability of the product, so much as it is that it's contributing to the instability of ATP, would be the electrostatic repulsion. And don't let the terminology for that fool you. This is just science for saying that negative charges don't like to be next to each other, and this is mostly illustrated by the fact that it has a -4 formal charge on the whole resonance hybrid structure there. So yeah, they're not going to like that. The other thing that's going to really contribute to the stability of your products is going to be resonance stabilization. So for resonance stabilization, if you look over here, and this is really for both ADP, I'll just go ahead and draw this out here, that we're talking about adenosine diphosphate, adenosine monophosphate, and then lastly just the inorganic phosphate that results from this cleavage here. If you remember, when we look at this, or remember back to organic chemistry when we talked about resonance hybrids, these molecules here are kind of fixated and trapped in these kind of locked up positions that they have here, with that negative formal charge being next to one another. Now, if with this terminal phosphate group here, and this is really not as so much contributing to the instability of it as is the fact that we have these two here that are kind of locked in place. And so there's less room for that negative formal charge to be distributed throughout the hybrid of your molecule, right? So if we cleave those bonds there, if we were to cleave this one here, there would be less negative formal charge in the molecule, and two, more room for the existing negative formal charges to move around. And then by the same notion, if we were to cleave this one here, there would be far less negative formal charge and a lot more room for him to move around than he is in this particular situation that he's in. So for ADP and for AMP, that is definitely appropriate, and if you could imagine what I just said there, I'm not going to redraw the structures out for this, but also in the inorganic phosphate itself has a lot of room for resonance hybridization. Just to draw this out of what one of the many forms that we can have for the inorganic phosphate. Really hard to draw lone pairs on this pen, so they're going to look really ugly. But anyways, both of these oxygen groups here are going to have negative formal charges, and in this context, this is what you're going to get as your structure for the inorganic phosphate. And this is kind of one of the main contributing factors, I guess kind of the driving source of resonance stability. And then the last thing that I wanted to mention that really contributes to the stability of your products is hydration stabilization. So when we, and this kind of connects to resonance stabilization as well, but when we look at the hydrolyzed forms of ATP, of either be ADP or AMP, this is going to increase the surface area for the negative, partially negative and partially positive ends of the phosphate group and water, respectively, obviously, to stabilize the overall structure of. You can see that, but the partial positive ends of the water from the hydrogen dipole interaction would help to stabilize this. Another thing that you may notice this is that at the terminal end here we have this -2 formal charge. That is usually 99% of the time, at least when we're talking about ATP, it's going to be coupled with the magnesium into +2 cation state. Is going to act involved in a lot of transfer and things like that. And so that's why supplement crooks are going to try to tell you that you need to take magnesium to increase your metabolic rate, which would, one, oxidize the shit out of you, and two, is not going to be absorbed systemically. It's a metal. It's just going to stress out your liver. But it does have a role in the body, and it is well recycled in the body, and this is what it has to do with.